Professor Federico Sanchez will give his talk about the lines of curvature of complex surfaces.
Okay. Well, first of all, I want to thank organizers because under these conditions, it's really difficult to find ways to communicate in a proper way. And I've seen the talks this morning, and I think they have been very nice. And we get the task, the goal of communicate this way. So this is very important that the effort all these people have done. Okay, so let's start with analyze the problem of lines of curvatures of compact surfaces of genus K. Since Farid have given a very nice and detailed, in some way, description of curvature lines in R3, of surfaces in R3, I just will very quickly show images the motivation of the work I'm presenting right now. Okay, so this work is a joint work with Vinicio Gómez Gutiérrez, a colleague of my university. So, well, let's start motivating. Okay, motivation lines of curvatures in surfaces in free space. Okay, this is very basic and elementary subject in geometry, and but it's interesting because it still has many problems, basic problems and difficult problems that are not solved. So despite of the very basic geometry, it shows a lot of subjects that you can work and you can contribute in an important way. So let's start just recalling what is a point, what is a curvature direction at a point P of a surface in R3, in 3 space. Well, this is very simple. Farid talked about it before. So is whether it's a tangent direction where the surface bends in an extremal way, maximal or minimal. So the principal curvatures are the values of these extremal bendings, the values that measure these extremal bendings. Okay, so I show you just a picture. So you have a surface, you have the point, and you have 2 directions in general. You can have also more, I will show, but in general, 2 directions, orthogonal in such a way the surface bends in a extremal way. You know, the numbers that measure at a point are called principal curvatures. See, for instance, K1 is the maximal and K2 the minimal. This is a classic subject, so it's easy. You study in the basic course in differential geometry, and you have any other direction. If these values are different, any other direction lies between the directions where the surface bends is not external. So you can have also umbilic points. These points are where the external bendings coincide. Namely, at any direction, the surface bends in the same way. So this is important because these umbilic points play a role that like a singularity in the foliation. So at each point, we define 2 principal orthogonal foliation or umbilic points where both directions, both curvatures coincide. So in this way, as Farid showed and gave some equations, we have in fact a foliation. In fact, 2 orthogonal foliations that may have singularities, which are at the umbilic points. So this is the general setting. For instance, we have curvature lines in the torus. You have this kind of behavior. You know, you have 2 foliations. One is look at the circles, small circles, and the others the big circles like that. At each point, you have orthogonal directions, a minimal direction, the maximal direction, meridians, and parallels that you have in the torus. This is well-known surface and configuration. So For instance, we have the sphere with two umbilics. In this case, you have umbilic on top and you have umbilic right here below, on bottom. So at each point you have, of course, here two orthogonal directions, maximal and minimal direction. And here there are umbilics, means that at this point, any direction has the same coefficient, curvature, principal curvature, the same curvature. So you have like a singularity in this way, because if you look at any direction you want to choose in the tangent plane at this point, you will find the same bending coefficient, which is the curvature, the principal curvature. So this is another case. We have other one, the curvature lines of Monge ellipsoid, which has this configuration, and in this case you have also this this case umbilics. This is 1, 2, and you have two more below that we cannot see. So this surface is a classic one studied by Monge and analyzed and developed by Darboux, who provide a complete description, the global description of this, analytic global description of this configuration of this foliation. Okay, so these are interesting descriptions because are complete and analytic of compact surfaces in this case. Okay, so Monge study this ellipsoid in the classic paper that goes back to 1796 and published this. So Latin American contributors about this on this subject are well known. Some of them are here: Ronaldo Garcia, Carlos Gutiérrez, now passed away, Jorge Sotomayor, and Farid Tari, and there are some others that we have contributed in this subject. So it seems like it is an interesting Latin American subject. Of course, there are other people who work in this, but this is some Las Americas Congress, So I want to point out specifically these names now, but there are some other interesting works. So interesting articles of these steps, the first steps of the subject, were written by Garcia and Sotomayor. This is historical comments, and for those who are interested in this history knowledge of principal curvatures, whatever, you can read them. They are interesting. And this other paper by Sotomayor, who describes in detail some interesting historical moments or comments about the Monge ellipsoid and interesting historical events related with this. So I recommend for those who like mathematical geometry history, just to have a look of these papers, okay? Well, the problem is quite about closed surfaces of higher genus. Okay, this is the problem. I have just already shown the ellipsoid and the torus, but what is the problem with higher genus? For instance, look at this, the double torus. You have this image, you have this, surface, compact surface with genus, with two holes, say. And we say that the double torus. Look at the expression of this equation that describes this model. So as you can see, you have two holes here. Okay, you have two holes here in this place. So you have to consider this radius, these quantities, and you obtain A and B, determining the centers of the radius of this, say the holes that define the holes. And you see that the equation becomes pretty difficult, pretty high, I mean, order 4. And when you try to describe the configuration, it's difficult. Because for this, as Farid showed before, I don't want to talk too much about it in the codimension 1, means in R3, you have to compute, in principle, first fundamental form, second fundamental form, and write an equation. And the coefficients become very difficult, and it's really, I guess, impossible to for this kind of algebraic models to obtain descriptions, precise descriptions of foliations. It's really difficult because the order is, algebraic order is very high when you work with the equations of principal curvatures. So we had this problem, and we tried to solve this problem with a different approach in order to describe this kind of foliations, not just for genus 2, but for higher genus. How could we do it? So I'm going to start showing that we pose the problem, this classical problem, first in R4. We consider immersions of surfaces in R4, and in fact, in spherical surfaces, means surfaces that live in S3 contained in R4. And these models comes from the real Milnor fibration that provides a lot of symmetries of these models and allow us to study and to reach the description of the corresponding embeddings of lines of curvature. This is the general idea. Let's try to show how can we use embeddings in of surface, a closed surface in R4, in order to describe first some principal configurations or curvature lines in these surfaces, and then how can we immerse again by the stereographic projection in R3 in such a way that we preserve the curvature lines. That is, we obtain embeddings in R3, in this case, for a very big family. In fact, a family which has a lot, all genus, realizes all genus, and description of this foliation. So this is the goal. The goal is to describe, to find a family of compact surface of any genus in R4, provided with a curvature lines in R4, and then realize them with an embedding in R3 with the curvature lines, and then reach the goal of the global analytic description of that. This is the panorama, the idea. So we start with this surface immersed in R4. Observe that we in this case is global, so the analysis is for closed surface. So we need oriented surface, and we consider the Riemannian metric, of course. And at each point of R4, we consider if this point is in M, the surface, we have split the tangent plane of M at this point and the normal plane of M at this point. So with this splitting, we have then the Riemannian connection of R4, which is not just the derivative, the covariant derivative of vectors. So what is that? Given local vector fields on M, we always can consider extensions of these vectors to R4 and define, using the connection, the standard connection, the Riemannian connection in R4, the tangent component to the surface. Then we obtain the connection on the surface, the usual way, okay? So we have then the second fundamental form of the surface in R4 in the following way. I recall that it's more or less similar to R3, but we have more codimensions. So I will write some equations, some elements to obtain the equation that I look for, which is the equation of curvature lines in these cases. So we need here tangent vectors, normal vectors to our surface in R4, okay? So the second fundamental form, it says this product of tangent vectors on M to normal vectors by means of the relation, the projection of the normal connection onto the normal bundle. you know, when you work in this codimension. So this map is symmetric and bilinear, and at each point, it only depends on the values on the point, because it's in fact a tensor. So, well, let's go to consider now a normal, an unitary normal vector field in this space, and consider the second fundamental form with respect to this normal in the following way. Take any point in M and tangent plane. So you define a quadratic form, take a vector here, we are just in a point, now we are not moving, just in a point, and send it by this vector, you obtain a quadratic form, which is consider the second fundamental form at the point, evaluated in x and the point at the point, then consider the dot product with the normal at the point. Okay, so this is a quadratic form. This form depends on the normal that you're under consideration. Okay, so very good. Well, this quadratic form has associated a shape operator, which is exactly the projection, the tangent projection of the derivative, the covariant derivative of the normal with respect to the tangent. Observe that we need to put bars because we need to have extensions in order to consider the connection in the ambient space. But in the end, in fact, it's something that depends on the values on the surface. Okay. Very good. So this is the self-adjoint operator. In fact, it's the adjoint operator associated to the quadratic form. So it satisfies these equations. And in this way, we will define directions, principal direction or curvature lines with respect to this normal. Okay. Very good. And then for each, this relation allows to say the following. There exists an orthonormal basis of eigenvectors of this operator, is nu, for which the restriction of the second fundamental form to the unitary vectors takes extremal values, maximal and minimal values. Look at, this is something similar what happens in R3. That's the same idea, but here in R4 with respect to a normal nu, okay? So we have more codimension, but if you restrict to a normal field, we have some like a similar construction when you work with quadratic forms and whatever. So the corresponding eigenvalues of this operator, shape operator, are called maximal and minimal curvatures. Look at the point that we say new principal curvatures. There are extremal values of the second fundamental forms that take value in some directions in a similar way that it happened for surfaces in R3, as I have shown some pictures. And of course, you can have the same thing, but with respect to a normal. So the point P is an umbilic if the new principal configurations coincide in the same way. It's similar, completely similar to the case in R3, but you have to consider codimension 2, and you have to consider just a normal, and the analysis with respect to the normal. Of course, it depends on the normal. Okay. So we have out of the umbilic set of the umbilic points, we have, as before, foliations, orthogonal foliations determined by principal directions, by the directions of extremal bending, and with values associated, principal values. The same stuff that we have had before, we have it right here, okay? But with respect to a normal direction. So this is what is principal lines of curvature or curvature lines with respect. Well, we have this set of principal lines with respect. Maximal, for instance, is a foliation with umbilics, which are exactly, you have to understand it like singularities. In the same way that we have shown before, but with respect to a normal. So this is standard. I don't think that we need to go to discuss too much more, because the machinery, all the elements I already present are very similar and just extensions of the phenomena that happens for immersions into R3, of surfaces into R3. So umbilics are considered as singularities of this foliation. Very good. This is the same thing, and we can obtain in the same way that Farid talked about before for the case in R3. We obtain a differential equation given it's a quadratic differential equation given in this form. I will write it below a little bit in some different way, but this is the stuff. You know, we look for eigenvectors. Look at here. These are eigenvector. X of p is an eigenvector of the shape operator, and lambda p is the eigenvalue. The extreme values or the curvatures occur in when it is not an umbilic in orthogonal directions, as I said. So this is the equation. We have the same stuff, and we have to keep in mind some pictures like I show at the beginning, but considering in R4 and considering with respect to a special normal direction that we have already chosen when nu is described by nu, the normal direction. Okay, this is simple stuff. Now, first part here, I will show how to obtain curvature, new curvature lines and equation when a surface in R4 is defined implicitly, which is important because this is the way we are going to define our surfaces. So we have first a proposition. If you consider a surface immersed in R4, and assume that it has two normals, a normal frame, and assume that you consider this vector, which is uniformized. I mean, you divide the norm in order to have unitary vector, normal vector, you know. So the new principal direction is given by this condition. We have what? We have two. See, if you have these two normals, you know, a normal frame, you have that to consider this product, which is the projection on the new principal direction on nu of this vector. Observe that this vector at each point is the value of a tangent vector, then the same normal vector, but when you derivate it with respect to the tangent direction, and you have the other vector in the frame, in the normal frame. So this is a condition that is easy to check, and you say the direction V is principal directions if it vanishes this equation. If vanishes this, it doesn't have projection on the normal vector nu. Then it is a new principal direction. Means that there is a maximal or minimal, an extremal direction. So it's a computation, easy computation to obtain this condition. Done. Now we consider M as a transversal intersection of the inverse image of regular values of two differentiable functions. So this is there is a natural frame to the normal boundary given by the gradients of each of the inverse image of regular values. So we have two, and since the intersection has to be transversal, we have in fact two normals. So we have two sets of principal curvature with this one with one normal, one gradient, and second to the other one. So let's write a proposition. Consider this. Imagine we have these functions from R4 to R, pair of real differentiable functions, and we assume that M is a surface defined at the transversal intersection of the inverse image of these two regular values. Okay. If we denote mu and nu, the gradient vectors of f and g respectively, we can describe the equation of new lines of curvatures of M given by this expression. This, well, of course, you have to develop, and you observe that we have a quadratic equation, and where the coefficients are given in this way. Of course, here the only thing is to observe that the condition that I wrote it previously in proposition 1 is expressed in coordinates in this way. You know, the components, say the components of the coefficients, say that you have in the quadratic equation that we have defined in this way. So you can obtain this description of the curvature lines with respect to nu in this case. Observe, nu is we choose this normal, the normal in this case. So it's computable. The point is that this is computable in R4. Despite that it might be difficult, you can use Mathematica and whatever, and you can compute this equation. Now, this is in general. You know, this is general for intersection, transversal intersection of inverse image of regular values of two functions. Now we are going to focus on Milnor fiber, you know, but let's do it the following way. First, observe that this proposition still holds if even we can admit some singularities, but the point is that the intersection, the manifold is regular. Say, have an idea, you know, not just to have an image. Yeah, everybody who has been these draws about Milnor fibration and whatever can see that this kind of things can happen. You know, you imagine that one of the equations, for instance, F is the blue one. It can be, for instance, a cusp, see, in R4. And the other one is the sphere, the three sphere. So it may admit a singularity here, one of them, but the intersection is not singular. It's regular, it's transversal, and a nice surface. Because it's transversal, you have to add codimension that you get a surface in the intersection of these two. So we have a pretty surface that I represented like this intersection, you know, in general. So then the equation that I presented just before, it is one, it holds also because we are out of the singularity. So we use the same equation, it holds, you can compute this, and you can obtain the equation in this case, okay? Very good. So we are going to use in this case this particular equation that is very fruitful. Okay, but before that, I want to add some interesting observation that we will use later. You know, to connect all these principal configuration with asymptotic lines of surfaces in 4 space. This is another set of lines. This set of lines does not depend on the normal as before, as new principal curvatures. These depends on the immersion only, and are obtained for those who knows that, you know, by the pullback of the second fundamental form of the surface of the lines that you get here from the origin to the curvature ellipse. How do you build? I just want to give some idea, the geometric idea of the phenomenon. If you consider a point on a surface, you can consider at this point the second fundamental form, as I did it before, and obtain in this way the image of the circle, unit circle. It will be an ellipse. You can have different possibilities of this ellipse. You can have this ellipse may be degenerated in a segment or in a point. When it is not degenerated in this ellipse and the origin is off the ellipse, the origin means the point itself, point P, when you are considering it in the normal plane, then you have two special directions. These directions are tangent direction to the ellipse, and their pullback are called the asymptotic lines. So observe that this is associated to the second order geometry because it's the second fundamental form that you play. So These lines are subject of study for immersions into R4 and very studied in different places and have also properties. And these lines are related with a new principal line in a special way in our models. I will show that. Property. For spheric surfaces, not totally umbilic, there is only one non-trivial new principal foliation, which means that it is independent of the normal. If you have a surface immersed in S3, contained R4, in fact, you can have one direction for the radial vector field, which is umbilic, of course, because it's spheric and the surface is itself inside of the surface. But you can have that other normal direction defined foliations, not trivial foliation. The point is that, in fact, there is only one foliation independently of this, the normal, okay? It doesn't change if you change the normal. And in fact, this foliation coincides with asymptotic lines. So when we work with asymptotic lines, with surfaces in S3, spheric in R4 in S3, we're working with foliations that are not depending on the normal. So in fact, only one foliation is the same as working with asymptotic lines. We will use these properties to obtain equations in order to provide a description I talk about of the configurations of the curvature lines on surfaces, using sometimes the foliation with respect to nu, sometimes the foliation to the description of equations of asymptotic lines according to our convenience, you know? So this is an important thing. Very good. So now let's go to work with this family of compact surfaces, which are links of the Milnor fiber, you know? We study. PPCAD study the topology of this kind of surfaces obtained at the inverse image of the orthogonal projections of holomorphic map on a line LA. The point is that this study, he studied topology and he gave some models to study, that allowed us to study the geometry of these geometrical foliations in this case. Consider a family. Let's try to show in a very simple way the construction of these families of embeddings, and then of the curvature lines, and then of the umbilic points, and all this description of the principal foliation of lines of curvature for these models. What is the construction? Consider a polynomial, very simple, from C2 to C the P, W, Q. The inverse image of 0 of the real part of F is a hypersurface diffeomorphic to a cone. The cone is described here by this intersection. I will denote it here at this point, TR, because it depends on the R. But in fact, the properties that we will show are independent of R. So, but this is the construction at the beginning. It's only the intersection of the sphere, as I said before. And here we have the description of the singular, of the inverse image of 0 of the real part of this holomorphic complex function. You know, this is in R4. We are looking at this in R4. This intersection provides the link. Moreover, the link of the imaginary part is the same. You have the same thing. So you have links for the real part, which is the intersection of real part of this equation of this function, sorry, and the intersection of the imaginary part of this function. The values are in C, so you have real part and imaginary part, and we have this. You take the inverse image of 0, and you have, in this case, the only singularity you can see very easily is the origin. Of the origin is a regular, and you have this intersection. This is the link of the Milnor, in this case, of this polynomial function. It turns out that these links are oriented surfaces of genus P minus Q, Q minus Q, okay? From now on, to simplify, we'll just consider R equal 1. And so we can obtain that these links, we can show, well, we can consider these links like surfaces, closed-oriented surfaces of genus P minus 1, Q minus 1, with this description, with using the real part or the imaginary part and the intersection with S3, which is the link of the Milnor in this case. Okay, so these are our models. Even more, let's specialize the analysis. Consider P equal 2 and this very simple model. Okay, this is quadratic in zeta and WQ. Okay, so in this case, also the formula gives us that this defines tori of genus Q minus 1, Q minus 1. So we have the torus, we have, torus, we have double torus, triple torus, all the pretzels, you know, we have all the surfaces that we are looking for, models for these surfaces. As the way I said before, I showed before. We have to consider the real part of the inverse image of 0 of these polynomials. So let's identify, this is a complex. We identify, as usual, the standard identification of C2 with R4. This is standard, very simple. W is U and V, zeta is XY, and express this under this identification, these functions from R4 now, with this identification, to complex. This is the real part, and this is the imaginary part. We have a function from R4 to C, and this is the expression of this. For this, for any Q, it's a family that realizes tori of any genus. Let's see. So, we have a sister action that you know that you naturally induced by the weights. We can define for each zeta. We have TQ omega, TQW, T2W, TQ zeta, and the action, this action, sister action, goes to the polynomials in such a way, this preserved, you know, the zeros are preserved, and you act in this way. So you have this, in fact, this is quasi-homogeneous polynomial preserved by the action. The zeros preserve the action. So even more, you can obtain a restriction of the action to S1, you know, instead of the whole complex numbers, you consider just the S1, and this action induces an action of S1 on the sphere, on S3, okay? So we write our function now. Observe that we have our function with values in C under this action. You substitute and you obtain what is the effect of this action onto these polynomials, and you get this expression. The real and imaginary part are polynomial functions with isolated singularity at the origin. The links are denoted like this as before, but now depending on theta. Theta is given by the action of the rotation S1, as I showed before. So observe that when you take the equal 0, we get exactly the real part, the link of the real part. And when you take theta equal P over 4Q, you get the link of the imaginary part. So you can see that how varying theta, moving theta, you obtain links moving according to all the same genus of surfaces, moving according to parameterized by the angle, but with the same genus, in fact. Then I will write quickly a parameterization of this family. So we project, we consider the case theta 0, the real part, and the case theta equals 0, and we have some symmetries given by this group according to these equations. You know, we consider this equation just from the equation of real part of a Q equals 0 equals 0, it means the inverse image. We obtain two equations. You just get very quickly, very easily, the equation that provide this inverse image of 0, and get this good coordinate chart given by these conditions. When x equal this for x and this for y, we have 2. And in fact, we define an homeomorphic polygon of 2H associated to the number q, which is the number of the degree of the polynomial, and we obtain, in fact, a boundary. What do we have? We parameterize here with an hexagon in the case q equal 3, corresponding to the case of a double torus. Remember that, as I said, the genus is q minus 1, so it's a double torus. In this case, we have a 6, 1, 2, 3, 4, 5, 6. This interior region is the hexagon, which parameterizes with projection the torus. So, and we have the parameterization. You just write square roots, whatever, and we use this parameterization. Observe that this is for T0, but when you compose with sigma, the action of S1, and project in the same projection that we use for T0, we obtain, in fact, that this coordinate chart parameterizes for all theta, because all theta are basically T0, but under the action of sigma theta. So we have this parameterization for this family that comes from the C-star action on the link. The main theorem. I'm going to write the main theorem. This is now we describe the umbilics of any of these links that you consider for Q. This is the link for Q. For instance, Q equal 3, this is a double torus. Q equal 4 is triple torus, and so on. So with this construction by Milnor fiber. So the set of umbilics consists of four points in the intersection of this surface with the XY plane, sorry. We can provide these points. So we determine in general, not just for the double torus, but for any genus given by Q, the umbilic points of the surface, only given by the intersection with the XY plane. So, moreover, we can describe the foliation, the local foliation. The local foliation, each umbilic has index 2 minus Q, 2 over 2, and it has Q separatrices and Q hyperbolic sectors. This is the, further I will show some image, but it's pretty simple. So how can we get this theorem? Because we use parametrization. Observe, we can control the parametrization with this 2Q polygon, and we apply this parametrization to make some computation of this general theorem. So the description of this umbilic and foliation, local foliation, in fact, involves and determine the description of the global foliation. I will show a little bit how it works. The proof is presented in 5 steps. I will try to show it more or less. An idea, of course, is deep, but I want to show all the tools that we use in order to describe this situation. First step, it is enough to analyze the case of TQ0. That means the torus of course, genus Q minus one, but when you consider theta equals 0, which means that this is the real part of the inverse image of 0, as I pointed out before, FQ. Why could we do that? Consider star identification as I did, and this is the action when you fix the angle theta. You have a product of two rotations of the plane, one of the XY plane and the other one UV plane. It's very, very simple. This is the first one. So we compute the normal with respect theta, This is the gradient, basically the gradient with respect to theta, and you have the computation and you obtain in this way. Observe how it plays the role. The first part is the real part of theta q, imaginary part of theta q, yes, so on. It depends. Of course, this gradient moves as theta moves with the action of theta of S1 on the link implies action on the gradient. So we have the computation. Observe that the gradient in zero, it transforms to this gradient by theta 2, theta phi sigma theta, sorry, and we obtain this configuration is transformed in the configuration given by nu theta. Okay, because it's an isometry and because the gradients behave properly. So this is the general idea. Of course, you have to give a detailed proof, but this is the reason because of it works. So we only need to compute to describe the lines of curvature for T0 for the real part, and you obtain the description of the whole links of the lines of curvature on the whole links. How to describe how to describe the intersection of T0Q with the X plane consists of 4 umbilics. How to prove that? We recall that we use the line of curvature with respect to nu, okay, that I showed before, and mu consider the radial vector field because it's the normal to the sphere. So we have the two normals, and we consider the gradients of both, and we consider the equation that I showed before. When you apply this equation, it happens that with these parameters, it happens that it vanishes. You have this because of the following. When you consider the covariant derivatives, you write here exactly for all q, for all q, the covariant derivatives, and you get this expression, and observe that these are, in fact, homogeneous polynomials, these 4 here, and of degree, high degree. This means that when you consider the XY plane, these have to vanish, okay? So the vanishing of these components imply that in fact, in the XY plane, the configuration that I showed here vanishes completely because you have these derivatives that vanishes for this normal, you know? Then vanish everything. Why? Because we are using these homogeneous polynomials in variables u and v. These are homogeneous. So when you consider xy plane, u and v has to be 0 and vanish this. This implies that the intersection of this plane with a link is umbilic point because it vanished this. So we obtain easily these 4 points as the intersection. It's just a computation, and you get these 4 points. And in fact, the only thing the final thing is to observe that are umbilic points for the case of 0, the real part. So finally, we get that globally, the action of the S1 preserves the XY plane. Okay, so these points move by the action of S1 just in the way I claim. You have to see how they move according to this action, the application of sigma theta. So this is only a rotation. I go back to say just here, just to show this, the statement, you know, this statement here. So you have here the way the action of S1 implies the transformation of the points. So when theta equals 0, we have 0, 0, 1, 1, 1, 1. And you have to combine all the signs, so we have 4 points. But when theta is different from 0, this moves according to the values of theta, okay? So this is the way, using the intersection to explain and the equation that I described here. Okay, let's go here. Okay, we're here, okay. And we observe that we get the second step. First step. Let's the description of the foliation. This is interesting because, okay, description of the foliation. We have the local foliation of nu 0 lines of curvature is given in this way. we have here, say, the description of the evolution at the umbilic points. So we have, this is the quadratic form, okay? And this goes to the coefficients that correspond in terms of the real part of zeta q, the real part of zeta q, and the second derivatives, okay? And the proof, I will give a quick proof of this lemma. But just to share, to show you that, in fact, here we have to, it's convenient to use now the description I show, the property that has to, that relates asymptotic lines of surface, of spherical surfaces, which is the case, this is the link. So spherical surfaces with respect to this. So we have this, yes, sorry, just 1 minute, please. We get this equation and obtain the local description of the asymptotic lines and compute and get that locally using this coordinate chart that I expressed before. We can compute the coefficient and in fact the differential equation. Okay, so we get the local description of the foliation in this case by means of the following analysis. We use the Darboux-Hope-Arnold results that implies that the associated to the which we call the quadratic differential, which is hyperbolic in this case, the differential of lines of curvature, which defines two lines, its kernel defines two lines out of the umbilic point. It is always associated, it has associated a vector field with twice the index of umbilic points. So in order to develop, to analyze this, we analyze, instead of the quadratic form, the vector field associated. And here we study, and this is the vector field as I show you, and we applied a polar blow up to the vector field I have here. This is the field associated to the quadratic form that I showed before, the lines of curvature. Okay, I finish showing that after some computation, we get the blow up, and we analyze the blow up of this, and we consider the separatrix polynomial and obtain solutions where you can find the separatrices, which corresponds to, in the standard way, to the singularities of the field that you left field that you got in the blow up. The interesting thing is that with all the stuff, we can compute determinant and show that this determinant in general is negative in these points. So we get, in fact, hyperbolic singularities. And this is the way we can check that these singularities have the description proposed in the statement, in the main lemma, which is only the Q separatrices, which are hyperbolic near to the umbilic point. Finally, I have to say something. The proof for the unicity of these points is still in progress, which means that in principle you can find that there were more umbilic points, and it would be difficult to describe then the global foliation. Nevertheless, to conclude, I show you that for the cases Q equal 3, 4, 5, means this is the double torus, triple torus of the torus of degree 4 of genus 4. We have that using coefficients of the equation computable in this case, and applying Grosvenor phases, we have that we can prove the unicity of this. The intersection of the zero sets of these equations, the coefficients of the equation of curvature, can be computed and provide that there are no more umbilics. So the structure of the foliation is given by the main theorem. So this is the basic results that I want to talk to you, to show you. Of course, the idea is that once we have this description for these cases, I would say just something that this is the goal, that to describe globally, because we have this description in the spheric surfaces, and if you apply a stereographic projection, you get immersions in R3 of these models, and principal curvatures become principal curvatures in R3. And I would say that this is a model that Darboux would like to see, if he would be happy to see with this description, because at that time they couldn't do it. And now, because at that time Milnor fibration was not studied, and here we see that if we work in these conditions, we can realize and describe completely, analytically completely, this phenomenon. So I stop here. I don't want to go further. And I thank you very much for your patience and to listen to me. Thank you.
Well, thank you very much for your pleasant talk. And does anyone have questions?